derivative operators, right? The S, the XS, f of x. This has to be member of the L2 space. Okay, this is overlap space. The S can be fractional. If you know how to do fractional derivatives, okay, those becomes the overlap half spaces. I give you an example on how to do half derivative, right? Most of you didn't get how to do fractional derivatives. Chris, do you know how to do fractional derivatives?
I don't exactly know.
Okay. So if you know how to do fractional derivatives, then you can define fractional overlap spaces. Okay. And also, in the real physics world, there's no delta function. There's something called a delta sequence. You can think of delta functions as actually due to a sequence of functions that becomes increasingly sharp. Okay, this is called a delta sequence. So we always do this mathematically for simplicity because this gives us a lot of nice properties. But think of in the real physics world, the delta functions look like that. Also similar with step functions. Step functions can be thought of as a sequence of functions that finally becomes like that. This is mathematically very nice to use, or very simple to use, but you can think of it as a sequence of that. Okay. So in the real world, things are always square integrable. But when we make idealization with step functions and delta functions, they become non-integrable. And also, if you ask me what use there is for group theory, you need heavy dosage of group theory to understand this theory. Okay, you have to have strong dosage of group theory, and also differential geometry. To understand this kind of thing. Okay, let's move on. Who is missing?
Tangent.
Huh?
Tangent.
Oh, tangent? Okay. Let's forget about him then. Okay, we always talk about basis functions. In computation, we have to expand things in terms of basis functions. And even if you use commercial software, you have to understand what basis functions are. A lot of you might not want to write numerical code, but just use commercial software. So it's good to understand what basis functions are. We can have orthogonal basis functions, orthogonal or orthonormal basis functions. And in that case, the inner product between these basis functions can be written as such. Okay, if they are orthonormal. And then if you have any function or any vector, you can, some people will call this a vector, the state vector, a function, a state function. Okay, all kinds of names prevail for this kind of thing. You will expand it in terms of, say, these basis functions in this manner. let's assume that this function is complete. Complete means that any functions that you have the square integral will say can be expanded in terms of this basis function. Okay? So they live in the same space. Then it's quite easy to show that I can take the inner product of this with Fm. Okay, I can take this equation inner product with Fm and use the orthonormal property, leaving behind just a delta Nm over there. And from this equation, I can get An is equal to Fn. Okay, can everybody see that? I make use of the orthonormal property of my basis functions. I take the inner product of the whole equation with f sub m. The left-hand side, I will get this function. Okay. The right-hand side, I will only have delta Nm left, and after using the property of the shifting property of this delta function, this is called a chronicle delta function. Okay, so I will just have one term left and have this. You see this? Okay, everybody sees that. That's good. So the general case is that if things are orthonormal, things are very simple, then I have f of x equals to n is equal to 1 to infinity f n of x f n of f. Okay? And this is orthogonal case, but if things are non-orthogonal, then things are a little bit more complicated. If the basis functions are non-orthogonal, then I wouldn't have this nice step over here. And if these are non-orthogonal, if I make the inner product with f, then what I have is that these summations wouldn't go away. Fm, Fn, An. I will have this kind of equation at this stage, if things are non-orthogonal. And then I can think of this as a matrix Bmn. So this is a matrix B dot A kind of thing. And then I can have this as, I can think of this as Bm. So this is a matrix equation, something like that. Then I actually have to find my A by performing a matrix inverse. Okay, this B is called a Gram matrix. It's called a Gram matrix. Okay. And you often see this name in use if you read the electromagnetic literature. But non-orthogonal basis functions are nice because they're easy to find. They're easy to find, easy to define. They are all over the place. Okay, orthogonal ones are harder to define. You can, of course, you can always make them, but they're harder to define. So there are some interesting things you can see. I think this is quite familiar to people in physics. But in general, if I have an f of x, I can expand things in terms of the basis functions in this manner very easily. But then I can also expand my basis functions in terms of another set of basis functions quite easily using the same formula. Okay, I can expand arbitrary functions in terms of these basis functions. Okay, this is the basis function. and this is also a basis function. Then if I put the two together, I have this interesting relationship. I can say that f of x is equal to sum of n m f comma gn comma fm f of mx, right? I can think of this as the identity operator, that this actually is nf let me see how I should say this. M I can rewrite this in this manner. I'm just rewriting the summations in a different manner. And you can see that this piece is the identity operator, which I defined to be I. And what I have done to obtain this relationship is to have inserted this piece into that piece over there. If I insert this piece into that piece and call this an M summation instead, no. That's not right. Okay, I have to write one more equation. Say.
Is f related to f?
What is that?
Is f of x related to f of x?
No. F of x can always be written as sum of m fm of x. This is just a basis function expansion, right? So if I insert this piece into here, then I get this relationship, Okay? So you can think of this as an identity operator. Is this the identity operator? And this is quite common in physics, okay? But maybe not as common in electromagnetics. So I just want to emphasize this point a little bit. So again, we use this space over here. Draw the arrow like this. So, but this is actually very similar to what we do in vector algebra. So in vector algebra, we will have something like this. We express a three-dimensional vector in terms of x, y, z as my unit vectors, but I can also pick another coordinate system and get a new representation of my vector in another coordinate system. But then the two are related, because I can say that this is just the fact that I multiply and this is my identity operator, formed exactly the same way as I did. You can think of my g sub n as my unit vector x, y, z. And then if I form that identity operator, I can multiply any vector a by it, I will get one representation. If I multiply by another representation, say ai prime dot a, I will get the other representation. You can think of ai hat as being equal to x hat plus y hat plus z hat. Those are unit vectors. You can think of ai prime as x prime hat plus y hat prime plus F prime, G F prime. Okay? So we see this in 3 vectors all the time, but it can be generalized to higher dimensions. So, from this you can derive the well-known Passer-Bayes theorem. Passer-Bayes theorem say if I have inner product between 2 vectors, and then I can define identity operator using different basis set. This is one identity operator that you can have. And then if I have another set of orthonormal basis set, I can also define another identity operator. It means that if I use this insertion, then I get this inner product G as an identity. But if I were to use the second one, I will get F comma G will be N, F comma Fn, Fn comma G. And this is just Passer-Bayes theorem. This is like saying that inner product between 2 functions is usually something like An, Bn in one system, and this might be An prime, Bn prime in another system. And what Passer-Bayes theorem says is that inner products are coordinate independent. Irrespective of what coordinate system you choose, you get the same answer. And you might have seen this written differently in electrical engineering. So in electrical engineering, we might have something like Ft, Gt, Dt, 0 to A is equal to maybe d omega, F tilde of omega, G tilde of omega, d omega. Okay, minus infinity. Then sometimes you might get a complex conjugation there. This is Passer-Bayes theorem. It's actually the same statement as this. Okay, any inner product is independent of the space that you write it in. Okay. I have more detail in the textbook. I wouldn't go into the detail. I have textbooks for sign series, Fourier transforms, and that kind of thing. I will use the remaining time to talk about something else. Okay, are there any questions regarding this? Because I don't want to go up on Passer-Bayes theorem too much. Okay, so we have talked about vectors, operators, and now let's talk about how we solve operator equations. Okay, solutions to the key actually is to convert operator equations into matrix equations and solve the matrix systems that follow. Since we have computers these days, this becomes a very important topic of research after the invention of the computer. Matrix algebra can be done by machines. Machines just have to repeat the calculation. So I can write an operator equation, as I said before, something like that. Okay. Then I can also write it more symbolically, almost like direct notation, saying that this is the vector, and G operating on the vector give me another vector H. Okay. Then I can insert the identity operator that I have defined, that I have erased here. I can insert this identity operator in there and get a new equation And then I can take this whole equation and find what the dual space of this equation is. That's very important. We just introduced the concept of the dual space. We want to multiply from the left with the dual space, functions in the dual space. Those are called the testing functions and weighting functions. So it takes some functions from the dual space of this operator equation and test them. And that then I will get this other equation, Wm Gn Gn F is equal to Wmf. And now I have a matrix equation because you can see that this is Gmn. This can be An, this can be Bm. So this is actually a matrix equation now. And this is an infinite dimensional matrix equation, but I can always truncate.
Should the right hand side be W, H?
Yeah, you're right. Yeah, thank you for pointing that out. Okay, so they become a matrix equation, something that you can compute, or send to the computer to compute once you truncate it. And you can perform this computation, and if the n is not large enough, you can increase your n to make the thing more and more accurate. This is usually called the matrix rep of the operator G. Okay. This is the matrix rep. So this is one way to convert an operator equation to a matrix equation. And at this point, I'd like to introduce how we define the transpose of an operator. What is the transpose of an operator? For a matrix operator, that's quite easy to do, right? Aij, you want to find a transpose, we just swap the indices, and that's called a transpose. But how do we do this for, in general, an operator that is defined abstractly? So we have to use definitions of inner product to define the transpose operator. In matrix algebra, we say that A transpose dot A dot B. If we take the transpose of this whole thing, this must be B transpose dot A, right? This is what we learned in matrix algebra. And instead of using this to define what the transpose is, we can use this equation to define what the transpose is. So in matrix algebra, we can use this to define what the transpose is. So the transpose of a matrix operator is an operator that satisfies this relationship. You can extend this transpose definition to infinite dimensional Hilbert space, that the transpose can be defined via this equation using inner products. Okay. Inner product of this and this should be equal to I think I'm doing it right. Okay, this is a scalar quantity. It doesn't matter whether I put a transpose or not, right? This is a scalar. So I can eliminate this transpose, because transpose of a scalar is itself, right? So this is equal to that, so this is equal to that. Okay? And you can go through more detailed derivation and prove that this is correct. And this can be used to define the transpose of an operator. Similarly, what about Hermitian or conjugate transpose? conjugate transpose. Unfortunately, I feel that this definition is very messed up in the math community. Okay, they often don't distinguish the transpose and the conjugate transpose. They call this a joint operator. So what we call Hermitian operator or conjugate transpose is what mathematicians call the joint operator. And they often don't distinguish between the real transpose and the conjugate transpose. They assume that there's only one kind of transpose, one kind of joint operator, which is not true. Because we know that in matrix algebra, there are two kinds of ways we can do a conjugate transpose. A conjugate transpose is when you do this in matrix algebra. Okay, this is called conjugate transpose. Okay. Instead of using this to define it, we can also use inner product. We define a conjugate transpose in matrix algebra will be equal to this times that. That is what we learn in matrix algebra. But then this is a scalar number. Conjugate transpose can be replaced by conjugation. Agreed? So you can extend this to Hilbert space and obtain the fact that the definition of conjugate transpose using my notation is this. Okay, not the mathematician notation, but I put this explicitly. Okay, so you can define this to be the conjugate transpose, and this is often called a joint operator. A joint operator, in my opinion, is a conjugate transpose operator, not just a transpose operator, a conjugate transpose. Okay, but mathematicians don't often distinguish these two. Okay, so these are some of the knowledge that you would need if you want to understand the electromagnetic literature. But let's talk about how we can solve an operator equation with non-orthogonal bases. Oftentimes, if you use orthogonal bases, you can define this identity operator. And you can get the matrix equation very quickly. But what happens if you have non-orthogonal bases? Which is often done in computational electromagnetics. Okay? So let's assume that we have a function, a vector function f, that we can expand in terms of a basis. The basis function g sub n. Okay, I will call this the basis function. I think in the EM literature it's often confused. People will always call this a basis. The basis is actually, if you look up the mathematical definition, basis is a set of functions. Okay, we shouldn't call this a basis, we should call this a basis function. The basis is a set of functions, but in the EM literature, people will call this a basis, which I think is a wrong notation, wrong nomenclature. Okay. So then if we plug this into the operator equation, then what we should get then is that we have this operator operating on g sub n, a sub n is equal to h. And we do the same thing. We find the dual space of this operator equation in test with W sub m, and making sure that W sub m is in the dual space of this equation. And then you get this equation, W sub m, G n, A n is equal to W sub m H. And then this again is a matrix equation. You can still call this a matrix representation of G. And you invert this matrix equation to find your unknowns. Okay? And if you choose the finite basis, like m is equal to 1 to n, the summations will be n. And you end up with the finite dimensional matrix equation. Okay, finally you get an equation that looks something like this, and this will be n by n. And n by n is a computable matrix, and you can send this to the computer to compute. So you start out with an infinite dimensional equation in Hilbert space. And you convert it into a finite dimensional equation. That is what all computation is about. So the key thing is how to find this as a good approximation. And this is the subject of approximation theory. Can a function in an infinite dimensional space be approximated with a finite number of functions? Is that possible? What do you think, Aditya? Do you think that's possible?
Depends on your error delivery.
Depend on what?
How much error you want to be approximated.
Yeah. Can I make the error exponentially small?
Then you'll have to have n to be exponential, right?
Allow n to be exponentially large? Actually, there are many examples that you find this is possible. We encounter this in electrical engineering all the time, in signal processing, right? If we have a function f of t, and we often write them as maybe a function that looks like that. And according to function theory, we need infinite numbers to represent this function. But in signal processing, we often don't. We try to replace this function with a finite set of numbers based on approximation theory that we know. Right? We only represent with n numbers. When is the bottom a very good representation of the top? What kind of properties do we use? Yes?
Nyquist theorem.
Nyquist theorem, very good. Nyquist theorem is what we learn in signal processing. What else? That the bottom one will be a good representation of the top one.
Do you need to use Parseval's theorem to actually?
Not really, not really. But there are certain things that which shows that this step is actually quite viable in many engineering applications. Infinite dimensional Hilbert space function can be replaced with a finite set of numbers. Okay, this is one example. Nyquist theorem is one, I guess. The important thing is that the function is smooth. If the function above is band limited, then you can prove that the bottom representation can be good to exponential accuracy. The error is exponentially small. How can we prove this? So you can think of this as being, let me call this f hat of t. F hat of t is f of t multiplied by an impulse train. Let me draw that as that, right? F of t multiplied by an impulse string gives me f hat of t. Then, if I take this to the Fourier space, this is the convolution of f of omega with an impulse string. What is the Fourier transform of the impulse string? Impulse string itself. So this would be convolving with impulse strings. The spacings are different. You have to adjust them properly. Okay, this is like crystallographic. You send X-ray to a crystal lattice. The X-ray diffraction pattern is also a periodic function. Okay, this is something you also observe in the real physical world. If you send X-ray through a crystal lattice, if you look at the diffraction pattern, it's also periodic. So why is that so? Does anybody know?
The far field of the diffraction grating is the Fourier transform.
Very good. Okay. If you send X-ray through a crystal lattice, the scattered field is a Fourier transform of the scatterers. The currents induced on the scatterers. Okay? And as a result, the far field is Fourier transform of the crystal lattice locations. And that itself is also a crystal lattice. You can see this, you can show this in 1D, 2D, and 3D, but this is true. Okay? The far field is always the Fourier transform of the currents. Does everybody know that fact? Aditya, do you know this fact? No? Okay, let me prove it to you then.